Welcome to Study Loop.
41.40. So we're told that for an ideal PN junction rectifier diode that has I guess a good boundary between the P and the N parts, that the current is related to the voltage across the diode by this equation. This is the Shoffey diode equation. I naught here is called the reverse saturation current. When the voltage is positive, it's called forward biased, and when it's negative, it's called reverse biased. And so the reverse saturation current is the maximum value the current will have when it's increasingly reverse biased. You see, this is going to go to 0, and so the current will be going in the negative direction, and it will have the value given by the reverse saturation current. So first we want to plot this for voltages between negative 0.12 and positive 0.12 volts, and with some parameters that they give in the problem to have actual numbers for these things. And then at the same 300 Kelvin temperature, wants us to find the ratio of the current when it's forward biased by 0.5 volts and reverse biased by 0.5 volts. So let's take a look at part A. So here's a plot of what this function looks like. It looks like an exponential. You can see down here, it's actually going negative, and this eventually, has an asymptote of the negative of the reverse saturation current. And so now we can look at this ratio. You can just call it like I plus and I minus, I guess. So we're going to have an I naught in both the top and the bottom. That's not going to matter. We're going to have the exponential of E times 0.5 volts divided by KT, where T is 300 kelvins, minus 1 . And then we'll have the exponential of negative E times 0.5 volts divided by KT minus 1. And so then this works out to be 2.5 times 10 to the 8th. So the going from half a volt reverse biased to half a volt forward biased is a 250 million fold increase in the current. They really don't like to conduct when they're reverse biased.